The modern periodic table numbers elements from 1 to over 100. The atomic number of the element tells you the number of protons in the nucleus, as well as the number of electrons surrounding the nucleus. The heaviest naturally occurring element is uranium, which has 92 protons in the nucleus and 92 electrons in shells out from the nucleus. Elements after uranium are unstable and are made in nuclear reactors. We arrange the elements in rows called periods. There are 8 periods here. The columns are called groups. There are 2 main groups on the left and 6 main groups on the right of the table. This table has 2 rows cut out and placed at the bottom. Imagine you use scissors to cut down after group 2 and insert the 2 bottom rows in place of the similarly coloured blank boxes. The resulting table looks like this, and the boxes are a bit small to read. This table consists of 4 blocks called the S, P, D and F blocks. This video will look at the most important elements found in the S and P blocks. Group 1 of the periodic table begins with hydrogen. Its soulmate is carbon. They both have half-complete outer shells. Together they share electrons, forming big molecules with powerful covalent bonds. This is a small hydrocarbon molecule called octane, found in petrol. Throw a few more light element atoms into the mix and we have the complex molecules of life with thousands of atoms. Diatomic hydrogen gas is a clean fuel which explodes when ignited in air. Hydrogen is also found in the acids, which we use for fun experiments with metals and alkalis. The group 1 alkaline metals are all silvery grey and soft with low melting points. We need to keep them under oil or argon gas to stop them exploding with water or air. With water, they form the skin-burning hydroxides that turn phenolphthalein indicator pink, as well as making hydrogen gas. Here sodium buzzes around a bucket of water, making hydrogen which ignites. If you get hit in the eye with a stray splatter of sodium metal, it may catch fire again. Potassium is even worse because the atoms are fatter and more reactive. It was the natural salt and alkaline chemicals that caused the ancients to name these elements. Seawater and animal cells are full of sodium chloride. Blood tastes salty. We have a craving for salt and eat too much of it. It can cause high blood pressure. The Roman name for sodium was natrium, hence the unusual symbol Na. Farmers know the importance of using potassium salts to grow vegetables. Plant cells have very little sodium and lots of potassium. Farmers learned to spread the ashes from fires onto crops. So the word potassium comes from potash, which contains the alkaline chemical potassium carbonate. The old Latin name was Kalium for the same chemical, hence the symbol K. Both potassium and sodium ions allow our brain cells to function. So make sure you eat fruit such as apples, rich in potassium. The group 2 alkaline earth metals are grey in colour and have 2 electrons in their outer shells, which they need to lose to form stable ions. They are less reactive than group 1 metals, but are still quite exciting. Magnesium is a silvery metal usually sold as ribbon. It takes lots of heat to burn, but when it does, the flame is very bright and should be viewed only through welding goggles. It burns very hot, and when hit with water or carbon dioxide fire extinguishers, it will split off the oxygen from these chemicals and burn even brighter. This property allowed magnesium bombs to kill tens of thousands of people each night in some raids over cities in World War II. The desperate firemen and people in shelters had little hope. Even so, magnesium is essential for chlorophyll formation in plants. Green chlorophyll makes the food that we all need to survive. Plant growers use Epsom salts or dolomite lime to encourage leaf growth. Calcium metal has fatter atoms than magnesium and so is more reactive. Touch calcium with wet fingers and it will burn you quite savagely. Heated strongly on a heat mat, it flashes with a scarlet dangerous flame. Its natural forms include calcium carbonate in shells, fossils, and the limestone that we use to make cement, or in calcium sulfate mineral, gypsum, that we use to make plaster in homes and plaster casts. Calcium salts also occur in our bones, which is why we should eat dairy foods as a source of calcium. The P block of the periodic table contains metals shown in blue, semi-metals shown in green, and non-metals shown in yellow. We will focus on the metal aluminium in group 3. Aluminium is a shiny silver, lightweight metal that is the third most common element on Earth. With an almost half-complete shell, it forms strong covalent bonds to produce hundreds of tough aluminium silicate minerals in the Earth's crust. Its main ore is bauxite soil, common in the north of Australia. This is refined to aluminium oxide called alumina. Aussie is the second biggest exporter of this material. The next step in making aluminium is a problem. Alumina melts at 2000 degrees centigrade, much hotter than a steel furnace. To reduce this temperature to a workable 1000 degrees centigrade, a rare fluorine mineral called cryolite is mixed with the ore. A great deal of electricity is needed to make molten metal in a Hall cell. The aluminium produced has a range of uses such as aircraft, lightweight engines, zinc-aluminum guttering and alfoil. But a word of caution. Living things do not use aluminium chemicals. Aluminium is a very reactive metal and will react with water if its oxide coating is removed. So when you use this stuff, avoid using alkalis such as cement powder and ammonia on aluminium frame windows. The recycling of aluminium metal products should be encouraged because it only uses 5% of the electricity that an aluminium refinery does. Group 4 lies on the boundary between metals on the left of the periodic table and a small handful of non-metals on the right. Carbon is a black non-metallic element that is the fourth most common element in the stars and the gas clouds that drift between the stars. On Earth, carbon is less common, and being lightweight, tends to concentrate near the planet's surface. In our atmosphere, we find small amounts of the greenhouse gases carbon dioxide and methane. Historically, these substances have helped warm the surface of the planet, keeping our oceans, rivers, and the water in our bodies liquid. Carbon is vital to life on this planet. With a half-complete outer shell, it forms strong covalent bonds with hydrogen and a few other elements, allowing giant molecules to form containing thousands of atoms. The living molecules that early life forms developed have transformed our oceans, atmosphere, and soils over long geological time. The study of how these processes worked and continue to change is urgent as man interferes with the Earth's natural cycles. The semi-metal silicon is a brittle grey solid which finds uses in electronic and solar panel technologies. It is extracted by heating very pure white sand with carbon in an electric arc furnace at 2000 degrees Celsius. The products produced continue to be used for good and evil in our rapidly changing throwaway society. Little appreciated as we destroy our biosphere is silicon's role in nature and forming the structural material for the Earth itself. Whilst oxygen is the most abundant element within the planet, silicon is the second most abundant. They form a partnership. 90% of the minerals within the Earth's crust are silicate minerals containing silicon combined with oxygen in tough, covalent network solids. The most famous of these minerals is quartz, which contains just silicon and oxygen. Harder than steel, quartz sand has a structure similar to diamond. Most silicate minerals contain pyramids called Silica Tetrahedron. If we add up the valencies, +4 for silicon, and 4 lots of -2 for the 4 oxygens, we get a net charge of -4. To balance this, silicate minerals carry lots of positive ions as well. Potassium, sodium, magnesium, calcium, iron and others, the elements of life. Feldspar is common in granites. It contains aluminium, potassium and sodium ions. This green mineral olivine dominates the mantle below our crust and is found in basalt. Basalt soils are rich in magnesium needed by plants and iron needed by plants and animals. Notice its structure. The pyramid-shaped tetrahedra are separate. The magnesium and iron ions sit in between the tetrahedra and are released to soils as the mineral reacts with water and weathers to brown clay. You might like to colour in these important elements on a periodic table and review in your mind some information about each.